Mr. Repke here, and we're going to continue talking about the counting principle, permutations, and combinations. Last time we talked about 5 students and they're getting in line. And we said, how many ways can those 5 students get in line? Well, we talked about there's 5 choices for who's first in line. There's 4 choices for who's second in line. 3 for who's third. 2 choices for who's in fourth, and 1 choice for who comes in last. We multiplied those together and we found there's 120 ways 5 students can get in line. We know that we can shorten this by using the exclamation point. We call that the factorial. And we even got a list of all 120 ways that these students can line up in line. Let's look at a different problem, and let's seat these students in a circle around a table. So we're looking from up above, and these are the 5 seats. So rather than being in a line, they're sitting in a circle. Now let's see if we can figure out how many ways they can sit in this circle. Let's just look at the most basic case. They sit A first, B, C, D, and E. If we wrote that out, A, B, C, D, E. Okay, there's one example. What's another way they can sit? Well, let's see. What if B sits down first, then C, then D, then E, and then A sits last? Writing that down, B, C, D, E, A. Now on the list, these look different. A's at the beginning here, A's at the end. But in the circle, we should notice that this is the same order. A is between B and E. B is between A and C. C is between B and D. D is between C and E. And E is between D and A. These two orders are the exact same if they're sitting in a circle. So we don't need B, C, D, E, A. Are there any other orders that would be the same for a circle that would be different if they were in a line? What if C sat down first, then D, E, A, B? Well, that's the same circle, only it's just starting right here. C, D, E, A, B. We don't need it. What if D would sit down first, followed by E, A, B, C? That's the same circle, starting here, going around. Now you see the pattern E, A, B, C, D is also the same circle. So these can get crossed out. If we did this for every unique combination and then crossed out all of, we'll call them the doubles or the repeats, we would find that there are only 24 ways that 5 students or items or things can be placed in a circle. Up here we said 5, 4, 3, 2, 1, 120. We can shorthand that as 5 factorial. I wonder if there's a way to figure this 24 out shorthand. 5, 4, 3, 2, 1 is 120. But 4, 3, 2, 1 is 24. Oh, okay. All we didn't need was the 5. And that is our trick. Anytime we want to find the number of ways a certain number of things can be placed in a circle, let's say 8, how many ways can 8 students sit in a circle? We just subtract 1 from the 8 and do the factorial. 8 students can sit in a circle 7 factorial ways. If we had 12 students, they sit in a circle 11 factorial ways. And that's Let's look at another type of counting principle. Let's say we go to a restaurant and they have 4 appetizers, and they have 7 entrees, and they have 3 desserts. And you start to think, man, if I was a cook here, how many different ways could somebody order an app, an entree, and a dessert? I mean, maybe they order the calamari, or maybe they order the wings, maybe they order the fish, maybe they get the ice cream, maybe they go for cake, who knows? We have 4 apps, 7 entrees, and 3 desserts. And all you need to do to figure out how many ways that somebody could order a meal, multiply those 3 numbers. 4 times 7 times 3 is 84. And that's how many different combinations there are of 4 appetizers, 7 entrees, and 3 desserts. Let's talk about Mississippi. Let's say we had each one of these letters on a separate piece of paper or a note card. And I asked you, how many different ways can these letters be arranged? Now, they don't have to make a word that's actually recognizable. We just want to know how many different ways can these letters be ordered. One thing we should notice is that we have a lot of doubles. If this S moves over here and those 2 S's swap, we have the same word. So these doubles are going to affect how many possibilities that we have. First, let's think about the line, the students getting in a line. Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So how many ways can 11 things be arranged? That's just 11 factorial. Okay, but that would be if they were unique letters, like A, B, C, D, E, F, G, H, I, J, and K. To account for the doubles, we're going to have to divide by the doubles. And here's what I mean by that. We start to look from the M, we don't have any double M's. But I do have 1, 2, 3, 4 I's. So I'm going to put a 4 factorial in the denominator for the I's. I have 1, 2, 3, 4 S's. So I will do 4 factorial for the S's. And I have 2 P's. So I will do 2 factorial for the P's. You might be able to just enter this into your calculator like this, but if not, we'll just do it. 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 4, 3, 2, 1 for 4 factorial. 4, 3, 2, 1 for 4 factorial. And 2, 1 for 2 factorial. Let's cancel some things out and make it easier. The 2's, the 4, this 2 and that 3 cancel with the 6. This 2 and that 4 cancel with the 8. And this 3 cancels with that 3. So now we've reduced it all the way down to 11 times 10 times 9 times 7 times 5. 34,650 ways that the letters Mississippi can be arranged. And again, these are unique ways. It's not counting if the S's swapped or the P's swapped or the I's switch positions. It would be unique words, well, not words, but orders, that 11 things, if you have 4 I's, 4 S's, 2 P's, can be arranged. You're watching the weather, and the 5-day forecast calls for a 30% chance of rain every single day for the next 5 days. 30% chance of rain for the next 5 days. What's the probability that it will rain exactly 2 of those days? So what's the probability that we'll get 2 days of rain? Here's how we're going to solve that. First, let's think in terms of combinations or permutations. Does it matter which two days it rains? No. We just want to know what's the probability that we'll get 2 days out of the 5. So that sounds like a combination to me. That means out of the 5 days, a combination where 2 of the days it rains. Okay? But even if we pick those 2 days correctly, we don't know that it's going to rain. There's only a 30% chance. So we set that up like this. 0.30, 30%, chance that it rains 2 days. And that's our exponent of 2. Because we're multiplying each day, the 30 and the 30, so the 2 days that it rains. But if I'm multiplying by the 2 days and the percentage that it rains, what about the days it doesn't rain? Well, if it rains 30%, what's the chance or the percentage that it doesn't rain? 70. Good. And we found that by just doing 1 minus the 0.30. And if it's raining 2 of the days, how many days is it not raining? 3. Exactly. So now we're going to calculate these and get our answer. And it might help if you do the 5 choose 2 off to the side. So I will do that. That means 5 factorial over 3 factorial, 2 factorial. That's 5 times 4. The 3's cancel with the 3, 2, 1 over 2, 1, so 10. So maybe it would be easier in our calculator in one long line to just put 10 times 0.3 squared times 0.7 cubed. And that will tell us the probability that we'll get 2 days out of rain out of 5. If we round our answer to 3 decimal places, we see we get 0.309 as the probability that it will rain 2 out of 5 days. And just a note, this means exactly 2. So it doesn't mean that maybe it rains 1 or 3 or 4 or 5. It exactly rains 2. 2 days of sun, or 2 days of rain, 3 days of sun. Let's stick with our same forecast, 30% chance of rain for the next 5 days. Let's do the problem slightly differently. What's the probability it's going to rain at least 3 days? At least 3 days. So you have to go back to English class a little bit and remember what at least means. If it rains at least 3 days out of 5, it means it rains 3 days. It could rain 3 days. It could rain 4 days. Or it could rain 5 days. At least 3 days of rain means 3 days of rain, 4 days of rain, 5 days of rain. Let's take our formula and set it up the same way. 5 days, 3 of them it rains, 30% chance it rains for 3 days, 70% chance of sun for 2 days. 5 days, 4 days it rains, 30% chance 4 days of rain, 70% chance 1 day of rain. 5 days, 5 days of rain, 30% chance for 5 days of rain, 70% chance for 0 days of rain. And let's go ahead and calculate those. Here are the probabilities that it rains for exactly 3 days, exactly 4 days, and exactly 5 days. And clearly I just round to 3 decimal places. So the problem asks for the probability it rains at least 3, and I've found exactly 3, exactly 4, and exactly 5. So how would I combine these into one answer? Well, I would add them. The probability of getting 3 days plus the probability of getting 4 days of rain plus the probability of getting 5 days of rain. So doing that right now, we get a 2, a 6, and a 1. So actually, it's not very likely that we'll get at least 3 days of rain, which is probably good. Let's talk about a different scenario. I have a jar. It has 6 red marbles, and it has 8 blue marbles. I'm going to reach in the jar and I'm going to pull out 3 marbles. And I want to know the probability that I pull out 2 red marbles and 1 blue. So this is my jar. I know I'm going to reach in and I'm going to grab 3 marbles and I want to know the probability that I pull out 2 red and 1 blue. Let's think about how we're going to calculate that. First of all, I need 2 reds out of the 6 reds. All right, so that's like picking 2 students out of a class of 6. And does the order matter? No, it doesn't. So that sounds like a combination. 6 combination 2. 6 factorial, 4 factorial, 2 factorial. Well, that's 6 times 5 over 2 times 1. So there's 15 ways that I can choose 2 reds out of 6 reds. Good start. Probably need to do that for the blues. That means 8, choose 1. 8 factorial over 7 factorial, 1 factorial. That's just 8 over 1, or 8. So there's 15 ways I can get my 2 reds. There's 8 ways I can get 1 blue. How would I combine these number of chances that we have, these outcomes? Well, we would combine these like we would do ways of ordering a meal. We would multiply. So there are 120 total ways of getting, or combinations of getting 2 red and 1 blue. So there are 120 total ways of getting 2 reds and 1 blue. 15 ways to get 2 red, 8 ways to get 1 blue. Multiply to find 120 ways to get 2 red and 1 blue. But there are other ways I can pull out marbles. I could get 3 reds, I could get 1 red, I could get no red. How many ways total can I pull out 3 marbles out of this jar? If I'm pulling 3 marbles out of a jar of 6 red and 8 blue, that sounds like I'm choosing 3 out of a jar of 14. All right, so 14 factorial, 11 factorial, 3 factorial. That's 14, 13, 12 over 3 times 2 times 1. We could reduce if we wanted to. 14, 13, and 2. There are 364 total ways of pulling 3 marbles out of this jar. All right, so there's 120 ways to get my 2 reds and 1 blue. There are 364 total ways of pulling 3 marbles out of the jar regardless of the color. So what's the probability that I can do this? What's the probability that if I reach in and I pull out 3 marbles that I do get the 2 red and the 1 blue that I want? Probability means what we want over the total. So 120 divided by 364. And if we round to 3 decimal places, 0.330 is the probability that I pull 2 reds and 1 blue out when I pull 3 marbles out of my jar.